Okay.
Okay.
I apologize for the delay. I seem to have some operational issues with the Surface PC. I think Dr. Chen said he had some problems with it last time as well. So there's no guarantee that this will not give a surprise after we get going again. And I hope I have my act together. I planned on getting back to Ames around 11 o'clock last night, but I was still in Washington, D.C. at that time. So it's kind of a short preparation on this lecture. Anyway, I'd like to talk about diodes today a little bit. If I talk fast enough, in spite of the fact that we've lost 10 minutes, I'll talk about capacitors briefly and then about MOSFETs. Does anybody have any questions before we start? Exam a week from Friday. And I had one email from the class about when the second exam is. I'll try to let you know when that second exam is on Friday. I think it'll probably be the Friday before spring break, but I will let you know for sure on Friday of this week. Second, we hope to have a review session next week. I will be on travel, and I think Dr. Chen will be on travel. So we'll probably ask one of the TAs to conduct a review session. But I'm looking for times. And we have a choice of doing it either Wednesday night or Thursday night if one of those two times would be evenings would be acceptable. How about Wednesday night? How many people? You can vote more than once. So if it's an acceptable day, then we'll look for a time. Wednesday evenings, how many people would be available?
Yeah, what time do you expect to start?
We'll work on that in a bit, okay? Okay, Thursday evening. It looks like quite a few more people are on Thursday evening. How early can we start on Thursday evening?
Anytime.
Anytime, 5 o'clock?
No, why not?
What?
That's 6.
Till 6 o'clock.
That's your fault.
6 o'clock Thursdays. Is that, how many people can meet 6 o'clock on Thursdays? Okay, we will try to schedule a review session next week at 6 o'clock on Thursday night then. Okay? Any other comments?
Oh yeah, is the homework for next week on Wednesday then?
It'll be due on Wednesday.
Yeah.
And it won't be accepted late. We will collect it in the class on Wednesday, and then we'll try to post the solutions right after that. Okay? Dr. Chen started talking about the diode last time. We looked at, it looked like a chemistry lecture for a little bit. We looked at the periodic table, and we saw that there's some interesting materials in a certain part of the periodic table, and that's the column where silicon appears. And silicon had 4 valence band electrons. And then we saw that to the left of that, there are 3 valence bands electrons in boron, and there are 5 in phosphorus, arsenic, and antimony. And these are used as dopants typically when we're looking for doped semiconductors. Almost always when we dope a p-type, we use boron, and when we dope an n-type, we use phosphorus or arsenic or antimony. The number of dopant atoms is what we're really interested in, so we can determine the number of electrons that are available to move from the valence band of one atom to another, but the diffusion rates and the orientation on the crystal are affected differently by phosphorus, arsenic, and antimony. So sometimes we'll use dominantly phosphorus or arsenic in the diffusions. Some of these materials that we use to make silicon ICs are pretty nasty materials. Some of the gases that we use to do the processing are highly toxic, and some of the materials that we choose to diffuse in are pretty nasty as well. There are some parts of the country that strongly fight the fabrication of silicon foundries because of the nasty chemicals that they work with. We talked about p-n junction. We saw that if we take a diffused N and a diffused P region and put them together, at the interface, we have ionization that occurs. And some of the electrons that are in the valence band of the N-type material migrate across the boundary and fill the valence band of the P-type impurities, and then we ionize that region in between. And once that region is ionized in between, we have basically an area where there's no charge conduction capability. We form a capacitance between the two sides. And we're going to see later, that this capacitance might look pretty lousy because it's voltage dependent. If we change the voltage on the junction, we change the thickness of that depletion region. But engineers are pretty clever, and you take something that says, well, it's kind of an undesired property that's dependent upon the voltage. Somebody says, hey, I can use that as a voltage variable capacitor. So we see a Bragg diode being formed right here when we just use a p-n junction and reverse bias it. We change the capacitance by changing the voltage on it. Now, it's interesting to note that this N-type material has positive ions. So there were extra electrons in the valence band here. When they move into the P side, they leave behind positive ions. So I just want to point out that there's the positive ions occur in the N-type side and the negative ions occur in the P-type side. And I believe this is where Dr. Chen stopped last time. Under forward bias of that junction, if you put a voltage from the P to the N side, we see that current will flow. And if we put a reverse bias on it, we see that the current is blocked. So we have an IV characteristic that looks like this. This is called the ideal diode model. And mathematically it's modeled by saying the VD is equal to 0 if the current's positive, and ID is equal to 0 if the voltage is negative. Okay? This is a highly nonlinear device, as well, as you can see. So we oftentimes say that the p-n junction serves as a rectifier. A rectifier passes current one direction and blocks current in the other direction. Let's look at an example. And I'm going to kind of wave my hands at the analysis of the circuit. So let's assume we have the world's simplest diode circuit, one diode and one resistor in series. And we put an AC voltage source in, Vm sine of omega t. And we can see that if the voltage is positive, we're trying to push current in this direction. So the diode wants to turn on, and our model shows the diode voltage is 0 when it turns on. So the output voltage equals the input. And when the input goes negative, we're trying to push current in this direction, but the diode blocks current in this direction. And if the diode blocks the current in this direction, the current through the resistor is 0, and hence the voltage is 0. So this is the output characteristics of the circuit if you have an ideal diode. And we see the rectification that takes place. It passes the positive part of the waveform and blocks the negative part of the waveform. These types of circuits are used a lot in AC to DC converters. It's the major element that's usually used, or at least in the past, in doing the AC to DC conversion. We're going to give several models for the diode today. Here's a little bit more accurate model of the diode. This is called the diode equation. And the diode current is equal to some constant IS times e to the VD over VT, where VD is the voltage across the diode from anode to cathode, minus 1. The parameter IS is oftentimes in the 10 femtoamp to 100 femtoamp range. Are those large currents? No, they look like extremely small currents. But if you look at the overall diode current, it's the product of something extremely small, but this is exponential. So what if VD gets very big? Then this quantity here can get really big, right? So there may be significant currents flowing through the diode, even though the parameter IS is very small. This exponential term could be made very big by putting the right voltage across that diode. IS is proportional to the junction area. So if we make diodes, we won't spend much time talking about making diodes, but we talked about how to make MOS transistors in the laboratory, and we can change the width and the length of the devices by the layout. Well, you do the same in the diode. If you make the diode bigger, the parameter IS goes up, and it goes up linearly with the area you allocate to the diode. The parameter VT is called the thermal voltage, and it's KT over Q, where K is Boltzmann's constant, T is the temperature in Kelvin, and Q is the charge of an electron. So K over Q, this coefficient here, it's a constant, and it's 8.6 E minus 5 volts Kelvin to the minus 1. Let's ask the question, what's V1, or VT, excuse me, at room temperature? Well, if you go back to this equation, KT over Q, and put in room temperature, maybe 300 Kelvin, you'll find the voltage VT, the thermal voltage, is about 26 millivolts. Now, oftentimes when you're operating a diode, if you're operating in an environment where you can wear a sports coat or a shirt in a room like this, the temperature probably won't change by more than 5 degrees C, or 5 degrees Kelvin. So the thermal voltage is around 25 millivolts over what we might think of as normal temperature operating range of the device. And since it's in Kelvin, not in centigrade, you can change the temperature quite a bit, and yet the percent change in the thermal voltage will be pretty small. So you can think of the thermal voltage a lot of times being around 25 millivolts. The diode equation is due to Bill Shockley, the inventor of the BJT, and he came up with this equation in about 1950. They had discovered the BJT experimentally. Shockley was a brilliant physicist. We talked about him earlier, kind of an abrasive type guy, but a brilliant type guy. When he was trying to understand how the bipolar transistor worked, he went back and first understood how the p-n junction operated. So he developed the physics behind it. It's interesting that the term diode was around since the 1920s. A person by the name of Euclides coined the term diode. In 1940, a guy by the name of Ohl stumbled on the p-n junction and observed that it rectified a signal. But he didn't understand how it worked. So about 9 years later, Bill Shockley figured out how that p-n junction operated. Kind of interesting that we have this p-n junction that serves as a rectifier, and we use it for a long time, but don't understand, we as engineers, but we didn't understand how it really operated. Okay. That's a good sign. That's even a better sign. So, see, how many models of diode do we have right now? We've got 2. We have that ideal model, and now we've got this diode equation model. If you plot the diode equation, you'll see it looks something like this. I've got a linear axis here. And since this is so nonlinear, until you get up to around 500 millivolts, the diode current is really small. But once you start getting up into the 500 millivolt range, for a typical value of IS, the diode current starts to get into the milliamp or tens of milliamp range. So if you look at this equation, we see that under reverse biased, when VD is negative, now this term gets really big for VD positive, it's very big positive. If VD is very big negative, this term gets extremely small. I mean, orders of magnitude less than 1. So for VD less than 0, we can pretty much neglect this term, and the diode current is simply minus IS. I don't even see it on this plot right here, because I've got a linear plot. Under forward bias, if VD is bigger than 2 or 3 times VT, the -1 becomes negligible. And we can approximate this equation by ID equals ISE to the plus VD over VT. We can neglect the -1. And it's only around VD equals 0 where we have to worry about that, either including this term or including this term. If you're very negative, you can neglect this term. If you're very positive on VD, you can neglect this term. Now, I'm going to make the statement that the simplification then is essentially identical to the model, except for VD equals 0. Essentially identical. If you look at this diode equation, even though it can be used for computer simulations, it's really unwieldy for hand calculations. Even the simplification of assuming that it's piecewise, it's minus IS if VD is negative, and it's this quantity here if VD is positive, even that's unwieldy. So let's ask the question, how much error is introduced using the simplification if the diode voltage is bigger than 1/2 volt? Okay. And to do that, what I'm going to do is look at the diode current with the exact diode equation, then with the simplification and take the difference and divide that by one or the other and see what percent change we get. So if I do that, the error, or the normalized error, is the diode current as given by the exact diode equation minus the approximation divided by the exact diode equation. And if I plug in VD equals 0.5 volts in that equation, I find that the error is less than 4.4 times 10 to the minus 9, the relative error. Is that a very big error? No. Our models are nowhere near accurate enough to even hint at seeing this difference. Okay. So, how much error is introduced using simplification? Well, we see the error is very small. It was 4.4. Oh, if it's less than minus 0.5 volts. So that's where we neglect this and just include the 1. And it's the same error, 4.4 times 10 to the minus 9. So the conclusion then is that the simplification is really good as long as VD is not real close to 0. Will you impress your colleagues or your boss if you use the more exact diode equation if VD is less than 0.5 or greater than, if it's less than minus 0.5 or greater than 0.5? Will you convince your colleagues, or convince your boss that you're a better engineer because you put more precision in your work?
Does it make a difference?
What?
Would it make a difference?
Well, it makes a difference whether you press your boss or not, right? If you press your boss, you might get more work assigned. You might get better pay. You might advance through the system more quickly, right? So it makes a difference if you impress your boss. So will this impress your boss if you're more accurate? I always use more accurate models. What's the feeling? What?
No.
No. Whoops, I missed it. Well, not only will you not impress your boss, you will unimpress your boss. Because then the comment is, did you really understand how these things worked? So you went and put this extra stuff in that didn't do any good anyway? Why waste time doing something that makes no sense anyway? So if you went and used this more exact equation, you didn't need it, you would unimpress your boss. You would impress your boss on the fact that you didn't really understand what was important or understand the model very well. Makes sense? Okay. So here's the simplification then, where we drop the -1 under forward bias, and we drop the 0, and we drop the exponential term under reverse bias. The parameter IS, we said was proportional to area. So I could write it as the product of JS and A. And the parameter JS is equal to some quantity. I'm going to call it JSX. It's a physical, it's a constant, not a physical constant. It's a constant dependent upon the process times temperature to the nth power times E to the minus band gap voltage of silicon over the thermal voltage. Typical values for these parameters, JSX is around 0.5 amps per square micron. M is around 2.3. And VG0, the band gap voltage, is about 1.17. It's a physical constant, characteristic of silicon. We observe that there's a somewhat obvious presence of temperature in the current then. One thing that is oftentimes done in a laboratory when you first work with diodes is we say, well, go measure the parameters of the diode. And one of the parameters of the diode is the parameter IS, right? So it's a nice experiment. Go in the laboratory, measure IS. That's pretty easy to do. If you know the area, then you can divide by the area and you get the parameter JS. So let me ask the question. What percent change in IS will occur for a 1% change in temperature at room temperature? If we go in the laboratory, we'd like to have repeatable measurements. We'd like to take a measurement now and tomorrow and get the same thing. Now and an hour later, get the same thing. Now and a minute later, we'd like to get the same thing, right? So if I asked you to go in the laboratory and measure IS for a diode, and ask the question, how much will change for 1 degree C change in temperature at room temperature? Would you have a 1 degree temperature change in the laboratory? As you guys are sitting in this room, how much has the temperature changed? How much has it changed in the last 5 minutes? Did you notice any change? No. Oh, I hear something. Does anybody hear? Does anybody hear that?
I think that's the projector. I'm just saying. It might be the projector. I don't think it's the airbag you're talking
So if it's a projector, why is, if it's a projector, usually you can hear something coming out of these little square things here too.
Yeah, no, I know what you're talking about, but I think in this case it might be.
So maybe that's my problem, but not the PC. So if you hear it in the projector, why would you hear it in the projector? Because of what? A fan. What do you put a fan in there for? So you can hear it? No. What?
Regulate the temperature of the...
Keep it cool, right? Blow air out. So as you're sitting here, very likely these have come on and off. Maybe there's been some additional heat that's been put in the room, and the temperature's been going up and down. Didn't realize that, did you? The human body has the ability to kind of ignore about 1 degree or 1.5 degree temperature changes. We kind of sense the average temperature, but we are not real sensitive to going up and down every few minutes. But it's doing that. If I had an accurate temperature sensor here, it's usually about a sine wave. When the heater comes on, it'll start going up a little bit, and then after the heater goes off, it goes down. You don't know when the heater comes on and off, but the fan might be running all the time, but we kick heat out and so forth. So there's a very sinusoidal waveform that's set up in almost all buildings, same as our laboratory. let's assume that we have a 1 degree ripple temperature. It could be more than that in the laboratory. So delta IS over IS, I could look at this coefficient at 1 temperature, at T2, and subtract the value at T1, and divide by the value at T1. And this gives me the relative change in the current. And if I do that, these J's and X's cancel, the A's cancel, and we get this expression on the right, and I can plug in now room temperature in that equation, and I find that I get a 21% change in IS for a 1 degree change in temperature. So if you were going to the laboratory measuring IS, you expect to be repeatable, what's going to happen? What's going to happen? It's going to change. So you hook it up, an experiment, you have the multimeter on to accurately measure the voltage that is proportional to current, right? Take the measurement. 20 seconds later, you take the measurement again. It's going to be the same? No, it's going to change a little bit or a lot. What? 20%?
20 seconds.
Could easily be. You should stand by it. So you have your experiment sitting here, and you come and stand by it. What's going to happen when you stand by it? It's going to get warmer. You'll be able to see it pretty easily. Okay, so the point I want to make is that this is not easy to measure. If you expected to measure IS precisely, you go in the laboratory and do it. Unless you take an instantaneous measurement of the temperature at the time you're measuring IS, you'll have a difficult time accurately measuring IS. If you look at the current when the voltage is positive, we often refer to this as the conducting state or the on state of the diode. And the other state, when it's has a nearly zero current, we typically term that the non-conducting state or the off state of the diode. If you look at that previous analysis I did, I kind of waved my hands at it. I kind of said, well, it's trying to push current in this direction, and hence the diode is on, and if the voltage is negative, it's trying to push current in the opposite direction down, won't let it happen. Let's try to be a little bit more rigorous in regard to that analysis. So I use things that weren't coming from Kirchhoff's laws or things that we had discussed in 201. I just kind of waved my hands at it, right? So let's look at a rigorous analysis. And that's not important only for diodes, but for other circuits, whether they're linear or nonlinear as well. Whoops. Somehow this PowerPoint is horribly slow. So let's try to calculate this output voltage. So we want to ask the question, what analysis tools can we use to analyze a circuit with a nonlinear element in it? Probably most of the time in 201, you focus on linear elements, resistors, capacitors, dependent and independent sources, and maybe the op-amp. Can we use KCL, KVL? Can we use superposition? Can we use the voltage divider equation? Can the current divider equation? Thevenin and Norton equivalent circuits. These were probably tools that you used a lot to analyze circuits in 201, right? Nodal analysis, mesh analysis, two-port models. Well, superposition doesn't apply for nonlinear networks. Voltage divider equations don't apply for nonlinear networks. Current divider equations don't apply for nonlinear networks. Thevenin and Norton equivalent circuits don't apply to nonlinear networks. So we have a nonlinear network here, or nonlinear circuit, and we're left with primarily Kirchhoff's laws and mesh or nodal analysis. So let's consider again this basic circuit. I'd like to analyze it. So I observe that Vn, I'm going to try Kirchhoff's voltage law, Vn is equal to diode voltage Vd plus the current ID times the resistor R. And I can observe that the output voltage is equal to ID times R. And these two equations come from the circuit architecture. And if I look at these two equations, I have the unknown ID, Vd, and Vout. So there's two equations and three unknowns. So I want to obtain the relationship between Vout and Vn. I need another equation. And I can look at the device equation. The diode current is given by the diode equation. And now I have three equations, and I have unknowns, Vd, ID, and Vout. So I should be able to solve three equations, three unknowns, and find the output voltage. So I have a sufficient set of independent equations. The good news is, in the simplest diode circuit, that I can solve these equations. And if I plug ID into these two equations, and then eliminate Vd, I find that Vout is equal to ISR e to the Vn minus Vout over Vt minus 1. I solved the circuit. What's Vout? I solved the circuit. This is as clean as the solution will get. Well, the problem is, Vout appears on both the left side and the right side of the equation. This is an implicit relationship instead of an explicit relationship. There does not exist an explicit relationship for the circuit. For the world's simplest diode circuit, we can get an expression for the output voltage in implicit form. But we cannot get an expression for the output voltage in explicit form. So even with the simplest diode circuit in the world, we have a closed form solution, but we don't have a closed form explicit solution. It doesn't exist. Wow. And the reason that we don't have, in this case, an explicit solution is due to the nonlinear nature of that diode equation. We solved a set of nonlinear equations and sometimes we're lucky. We have circuits with nonlinear equations and we get explicit relationships between inputs and outputs. But in this circuit, we can't. If I look at more complicated diode circuits, more resistors, more diodes, more components in there, things get a lot worse real quickly. So simplifications are essential if we want to obtain analytical results in even very simple diode circuits. So let's study the diode equation a little bit further. We plotted the relation of the diode current and the diode voltage, and we saw this current with a linear axis that grows exponentially. We don't see it back here growing exponentially. It's growing exponentially back here also. But the current down here might be in the nanoamp range, in the picoamp range, in the femtoamp range, and so forth. Now, if you look at the diode, the power display of the diode is the product of the voltage and current through it. So if the voltage went up to 1 volt and the current went up to 10 kiloamps, the power dissipation in that diode would be 10 kilowatts. We could use that diode for the heater to heat this building if you put 1 volt across it. Well, the diode will destroy itself because it will get too hot if we try to put that much current through the diode. So we typically have to operate at lower voltages on this device. Let me replot the relationship between the diode current and the diode voltage now with a linear log axis. So I have a logarithmic vertical axis and a linear horizontal axis. And if I look at this plot, I notice that for a 2-decade change in current from 0.1 milliamps to 10 milliamps, that's a big range of current, isn't it? A 2-decade range in current, the voltage is always around 0.6 volts. It might change from about 0.57 to about 0.63, but it's around 0.6 volts. If you look at applications of the diodes, this is usually the most useful current range when you're having a diode conducting. So now let me return to the linear axis, observing that the region we use the diode in, if it's going to be conducting, is usually between, 0.5 and 0.65 volts or something, or 0.55 and 0.65 volts. So I could come up with a new model, and that it's bad when the PowerPoint slide is slower than the human voice. This is a new model, and this approximates the actual diode equation. Okay, so this is our third model. We start with the ideal diode model. Now we have the diode equation, but it's too complicated to work with it. Now we've got another model shown by this blue curve that does a reasonable job of approximating that IV relationship of the diode. This is called a piecewise linear model. It's called piecewise because here's one piece, and here's the other piece. And it's called linear because in this region here it's linear, and in this region here it's linear. So when you say piecewise linear, it refers to two important properties. It's defined differently in two different regions, and they're both linear. So if I want to mathematically express that piecewise linear model, I can say the diode current is 0 for VD less than 0.6 volts, and VD is equal to 0.6 volts for ID positive. So that's a mathematical expression for that piecewise linear model. Here's the equivalent circuit. If it's in the off state, current 0, so it can model by an open circuit. And if it's in the on state, the voltage we said was 0.6 volts. So here's the equivalent circuit for this piecewise linear model of the diode. Here's a better model. What have I done here? Yes? What have I done here? I'll bet you can't make that happen. Well, I put another approximation in. Does this line do a better job of approximating this curve than the one we had before? Maybe a little bit. Okay, so this is another, what kind of model? Piecewise, linear, and it includes a resistance of effect of the diode when the diode's in the conducting state. So it's a little bit better model in the on state. So you can say ID equals 0, then for VD less than 0.6, that stayed the same. But for VD bigger than 6, it was a line that had a certain slope. And the slope was 1 over RD. So we can express it in the on state as 0.6 plus ID RD, if ID is positive. And here's equivalent circuit for the diode in the on state using or including that slope effect. Of course, I didn't give a mathematical model for the ideal diode that we talked about earlier. I'm giving it right here. In the on state, a short circuit. In the off state, equivalent circuit was an open circuit. So we've had 4 models. We had the ideal diode model. We have the 0.6 volt piecewise linear model. We have the piecewise linear model that includes the resistance effect in the device. And we have the diode equation model. Which one should we use?
Depends on your operating voltage.
Not too much, not largely. Not largely. Well, the flippant answer is the simplest one we can get by with. And that's the good news. The bad news is if you use a simple one, how do you know if you can get by with it? It's kind of the chicken and egg problem, right? I put in a simple model. I analyze the circuit. Then I say, gosh, is this accurate enough? Well, one way to find out if it's accurate enough is put the more advanced model in, analyze the circuit. And if there's no difference between the simpler model and the more advanced model, then you can buy the simpler model. Well, what's the problem with that? You already use the advanced model. So you might as well use the advanced model and forget about the simpler model. There's another way, though, that we can get around that problem. So we'll mention that. Does anybody see another way to get around the problem without putting the advanced model in? We'll put 2 simple models in. For example, if we use a 0.6 volt model, we'll put in 0.6 volts. We'll put in 0.7 volts. And that bounds the transfer characteristics between those 2 models. And if there's not much difference between what we get with those 2 simple models, we'll say either one is good enough. And we don't need to go to the more advanced model. Does that make sense? So there are ways that we can determine if a simple model is adequate without putting in the more advanced model. Any questions? That's all for today. Thanks.
I didn't mean to correct you in front of everyone.
No, that's fine. That's fine. You're probably right. I heard it, and I didn't realize it was coming from the ejector. I thought it was from the fans.
Either way, you got your example, though. You got your example.
No, by the way, don't ever be hesitant about correcting me on anything. I'm certainly open and I welcome it.
Probably won't happen again, though.
Thanks. I talked to you at the beginning of the semester about my disability, just with extend time on
Yes.
exams. So should I just send you an email about that? Or
Send me
what
an
should I-
email and I will take care of it.
All right, sounds good. And I also talked to you at the beginning of the semester. I have a couple questions.